All right, so today what I want to talk about is I want to answer any questions you might have about the dot product stuff. That is something I want to talk about specifically with regard to that, which is, and then I'm going to talk about that. This is 12.3, and then the cross product, which is 12.4. And then I'm going to be running, this is a note to make up for the fact that the last couple of weeks, especially the last week was really weird because I was out for a couple of days. I'm going to run an in-person office hour tomorrow, say tomorrow. I'm going to run office hours tomorrow. You guys are welcome to come and hang out with me anytime between 1 and 3 p.m. I'll just be in the downstairs outside my office. It's in person. This is like an additional one. I think normally I got one at 11 o'clock or something on Wednesday, but this is a better time for collection. All right, before I start, are there any questions? Okay, now it was pointed out to me that I posted a video that was incorrect, that my 10.3 video is actually like the wrong video. I will fix that as soon as I get a chance to get on my computer and fix it. So if you were waiting for that, although that's stuff I did in class, so probably not relevant to the people who actually come and watch me talk in person. Are there any questions I can answer before I get started today? Yep.
So I feel like working on like the graph of one of the when find some of the vectors.
Sure.
So when if you're given A, right, and it goes look and X, Y, and Z is your thing, A goes here.
Yeah.
But then when you look at B, it's not like you're just saying, okay, B is this position. B.
Okay. So kind of what you're after here, I think maybe is the fact that vectors are supposed to be translation invariant, right? So if you have a vector A and you have a vector B, one way to write them is like this, right? You have A and you have, say, B. This may be driving, I think this is what you're driving towards, right? When you think about vector addition, right? So you say, well, if your question is, how is it possible to add these when they're not set up correctly for adding? Is that what you're going at, or is this slightly different?
Or it's more of like, you're given you're given the numbers for everything.
Sure.
And you add them up and you find the sum.
Yeah.
So sum makes sense, but it's just B itself when you're drawing on the graph. It's not like it's not like with A where you draw to a point and say it's at this point. It's more of like it's a translate, like it's
so the big picture here is that vectors are translation invariant. Well, fancy name. Means they're the same no matter where you slide them, right? That it's not really a vector. A vector doesn't have a fixed anchor point, right? Conveniently, we can locate them like this, but I could just as well, if I wanted to think about the vector A and the vector B in that setup, and it wouldn't matter, right? Because remember, vectors are just measuring, vectors have two pieces of information. They're not telling you where you are in the plane. They're telling you what direction to go and how much magnitude is contained in that, right? So it doesn't matter where the anchor point is. A vector encodes two pieces of information, direction and magnitude. And neither one of those requires that you know where they start. That's why they're translation invariant. So when you do A plus B, the picture can look a little weird because if you put A plus B on this picture, right, it looks like this. Right, so this is the weirdness that you're talking about here, where you can plot the vectors and you get this picture out, but the point is you could arrange this picture so that it looks like this, right? So the vector addition that you get from summing the components is the vector that you get by setting these things up tip to tail like this, right? And so that's actually why a lot of times this has a special second name, which is resolvent. So they say the resolvent vector, what they mean is take the second vector and hook it up with the first vector and then connect the tail of the first to the tip of the second, right? So all of this sort of encodes this translation invariance. I don't know if that's your question, but the geometry going on in the background is that vectors don't care where they start. Anything else like that I can answer? I guess, yeah, the weird thing is, so what I'm saying is, these are the same picture. They don't look like the same picture, but they are. This is the weirdness of vectors. It's that vectors don't care where they actually begin. You can usefully slide them around. I mean, hell, that's what, like, every time you're in a physics class and you're doing one of these guys, you're like, oh, well, there's some component this way. And there's, I mean, you're just choosing convenient vectors to be located in the object you're studying. But then as soon as you reorient that into a right triangle to decompose it, you're just doing this. Okay, so now, one of the things I want to emphasize here about vectors that for people maybe who have not watched the video, so I guess we should say here, 12, just to tell you, 12.1 and 12.2 are sort of basic vector arithmetic, which I don't think is particularly challenging. It's just obnoxious, right? You can, I mean, it's really just obnoxious. Calculating vector magnitudes is obnoxious. 12.3 has some important ideas inside of it. This is the dot product section. And the really big ideas that I want you to take away from the dot product section are the following. If you have a vector A and you have a vector B, say these are vectors, and notice, I'm not telling you that if they live in R2 or R3, because the rules are going to apply in either case. Actually, they work in any number of dimensions, right? The rules I'm going to write down. The first thing that is very useful oftentimes is that if you take a vector and you dot it with itself, you get the length of the vector squared. That comes up all over the place. That's just from writing down what the computation of the dot product with itself is, right? If these were in R3, this would be A1 squared plus A2 squared plus A3 squared. The length of a vector is literally that. And if you take the square, kill the square root. I mean, that's kind of what's going on there. This is an important one. The other thing that shows up all the time when you're working with vectors is the way that you define what it means to be orthogonal. And really, you can substitute the word perpendicular here, and you're not really nothing. You may have had teachers in the past that insisted on a difference between orthogonal and perpendicular. They're basically the same word from two different roots, one from Greek, one from Latin. It's basically the same. So don't offend me if you say orthogonal when I'm on perpendicular. The idea here is that two angles are at a right angle. Okay, A is perpendicular to B. That happens precisely when we got the nothing. So the dot product is a way of measuring when things are at right angles. One of the most useful features of the inner product of the dot product vectors is it tells you when things are perpendicular to each other. And the reason that it does that is because of point 3. So I guess what I want to say here is this means that the dot product contains the length of vectors inside of it. So dot products contain information about length, but they also contain information about angles. This is information about the angles between two vectors. And we also have the formula that A dot B is equal to the length of A times the length of B times the cosine of theta, which is the angle between them. A, B. So dot products contain information about length. They also contain information about angles. Useful thing to want to know about the geometry of vectors. This is why we learn this. Because physics is built out of vectors, and I need a mathematics that like helps me work with vectors efficiently. The proof of this is pretty cute. It's laid out pretty well in the book that this relationship is true. Okay. All right. So that's kind of the basics of the dot product I really want you guys to carry away. There are vector projections are defined in here, but that's not something you really need until you're working with it. So you need to learn it. You should go back and watch my video, but I don't want to belabor it in here. Okay. It will come up if we apply it in chapter 13. I'll go through what the vector projection is. Yep.
Is the length just like magnitude squared?
Yeah. You should think you're like, when I say length, I really mean magnitude. And I'm not saying it is the length, I'm saying it contains information about the length. I mean, this is the magnitude of the vector squared, is the dot product of the vector with itself. Right, so all I'm trying to indicate here is not that it's literally length, but that it has information about magnitude or length. So another thing you might, okay, so I think I've told you guys before that secretly underneath it, a lot of this math is either in n dimensions or in complex numbers. The same rules actually work for complex numbers, it turns out. There's a notion of dot product for complex numbers that also contains information about angle and magnitude. And this idea works for vectors in any number of dimensions. You want 10-dimensional vectors, the same idea still works. It's harder to say what an angle means in 10 dimensions. You can't visualize it, but still, just if you rotated one vector to the other one, how many radians would you go through to do it? That's what you're picking up here. Okay, now notice implicit in this is the idea that I'm hoping that people have actually watched the videos on at least on 12.1 and 12.2, because I'm not intending to cover that in the lecture because it's arithmetic. So if there are questions about that, you need to make sure that you read and ask me. Okay, okay. So this is the big deal with dot products. I'm going to reiterate. Dot products contain information about magnitude with this formula. They contain information about right angles or orthogonality with this formula, and they contain information about angles with that one. Those are all big features of dot products that you need to have. All right. Somebody told me it would be blazing hot in here today because it's cold outside and the people downstairs turn their heaters on. I don't know if it's warm or cold. I'm getting cold at the same time. Okay, so the weird thing about the dot product is that it's not the only way to multiply vectors, right? That's really what a dot product is. A dot product is a way to multiply vectors. It's kind of weird. The other name for the dot product is the scalar product, because you put in two vectors and you get out a number, right? That's weird. It's like you've destroyed the vectors. Oh, I got two vectors in and I multiply. And when I multiply two numbers, I get another number out the other side, right? So it turns out there's another way to multiply vectors. So there's a vector product. And the way the book motivates the vector product is kind of lame. It says, oh, look, we'd really like to be able to produce an orthogonal vector from existing vectors. That is not what the motivation for this was originally, which I will show you when we get there. The vector product you've probably seen before with the name cross product. Cross product of vectors. Okay. And the idea is that it is a vector product because you feed in two vectors, and what comes out is a vector. So it's another multiplication. Calling it a product or a multiplication is justified because it satisfies all the rules we expect a multiplication to satisfy. We wouldn't call it a product if it didn't act like multiplication. We even go so far as to use the multiplication symbol for it. So the big feature of the cross product, so before we talk about computation, I want to talk about what the cross product actually is. Okay. Because it's kind of their definition of what's going on here is completely backwards. So how far do they actually get it? They don't even tell you where it actually came from until 3 pages in. Okay, so this is where the cross product came from, why it exists originally. So imagine you have a vector A and a vector B. A. Turns out to be the case that if you complete this into a parallelogram, so what do I mean by that? I mean, if you go down the diagonal of this vector right here, which is A plus B, is the diagonal of a parallelogram. This is very badly drawn, where B is on this side, and there's another copy of A right here. And this vector that runs across the middle is a plus b. That's the geometric picture of what's going on here, right? There's a parallelogram that is defined by adding a and b together and using a plus b as the diagonal. And you can pick up b and stick it up here. That's like a plus b. Or you could do b plus a. You should get to the same place either way, right? So if you run this way, it's like a plus b. If you run this way, it's b plus a. Same thing. So it turns out to be the case that the whole purpose of the cross product, and everyone in here has seen the cross product before in some setting, is that it tells you what the area of that parallelogram is. So the cross product of A and B is defined not to make orthogonal vectors. But the definition of the cross product, which we'll write down in a second, the definition of the cross product is defined to give you the area of the parallelogram. So the area contained inside of that is the absolute value of the cross product. Area is equal to the magnitude of A cross B. This is the big geometric feature of the cross product, why it exists. The cross product exists to tell us about this parallelogram. It has a bonus feature, but that's why it exists. Okay, so now what is it? Okay, so first rule, cross product only exists. Only exists. So only three-dimensional vectors have a cross product. You might ask, is there some way I can make a beefier kind of thing like a cross product in higher dimensions? And the answer is yes, but it's really hard. Okay, so the cross product is a thing that happens only in 3 dimensions. So suppose A, A1, A2, A3, B, B1, B3, where these are 3D. Then, the cross product of A and B is defined to be A2, A3, A2, B3 minus A3, B2, A3, B1 minus A1, B3 and A2, B1 minus A1, B2. I got this backwards. This is A2, B1. One, two, 2 before 3, 3 before 1, 1 before 2. Yep. Now that's an ugly formula, hard to remember. But this is chosen specifically so that you can actually figure out using a long-winded computation that this particular definition gives you when you take the magnitude of that vector, you get the volume or the area of this parallelogram off the other side. It just sucks to remember, so don't remember this. There's a better way to remember this. Don't remember this formula. We're going to use the determinant of a matrix to remember this instead. Okay. Now, I can't really justify why matrices get involved and why there are determinants, other than the fact that it is a convenient computational tool used to write down what this actually is. So, keeping in mind that the whole point of this, is to produce this area, which is why this odd definition was chosen. If only there were a convenient formula. So this is going to seem like a tangent, but it's not. We're going to talk about the idea of matrix determinant. But to remind you guys how a matrix determinant works. So matrix determinant, a matrix is just a square of numbers in our setting. And the determinant is just a number. Number you produce with the matrix. You go on in linear algebra, you'll learn that this has a really special set of properties associated with it. For us, it's just a way of putting a matrix in and getting a number out. So I'm just going to define the determinant of the 2 by 2 matrix. The determinant of the matrix A, B, C, D, this dude right here is a matrix, array of numbers, is defined to be AD minus BC. Now you might ask, where could that possibly have come from and why does anybody care? Which is a reasonable question. How's that? Yeah, it's AD minus BC. Okay, so it doesn't actually come from the cross product itself. For those of you who are, remember I told you the division doesn't exist, there's only multiplication by inverses. This number tells you when this has an inverse, when you can divide by this matrix, basically. So if you take linear algebra, if you take 206, one of the things you're going to learn is one way of measuring whether or not a matrix can be divided by is related to this number not being 0. All right. So this is a quick example of computing a determinant. Most people in here have seen before. I imagine if you did something like 2, 3, minus 1, 6, and you calculate a determinant, it is A times D minus B times C, which in this case is 12 plus 3, which is 50. It's some number. The number. Okay. So what we're going to do is we're going to take this definition, which is very easy, and we're going to build it up to a definition of determinants of 3 by 3 matrices. So I apologize if this is review, but if you've never seen this before, this is utterly mystifying, I think, where this came from. So you define the determinant of a 3 by 3 matrix. They're going to use these symbols. Write the determinant symbol out here. You define this determinant by using 2 by 2 determinants. So the idea is that this definition turns out to be this number times the determinant of this little matrix right here. A1 times the determinant of B2, B3, C2, C3, minus A2 times the determinant of the matrix that's left over when you do this, is B1, B3, C1, C3. I'm going to write this like up higher. It's ridiculous. This determinant is A1 set of B2, B3, C2, C3 minus A2 times the determinant of B1, B3, C1, C3 plus A3 times the determinant of B1, B2, C1, C2. This is definition. This is a way of defining a number I can attach to this matrix in terms of these where I gave you what the definition was. This is called the recursive definition. I started with something concrete, and then I say, oh well, the way that we do the way we do the 3x3s is in terms of this formula for the 2x2s. Now, I'm not going to work this all the way down to a pile of symbols where I compute these as well, because I actually want to apply this formula to the computation of the cross product. And this is as far as we need to go for that. Before I do that, let me compute an example determinant for a 3x3 matrix. Okay, so let's do something like, so when I'm drawing these straight bars here, straight bars around a matrix mean take the determinant. That's why I keep confusing myself by writing the bars and then having to add the determinant back in. So I'll try to make sure I put it here. So I'm being utterly clear that what I'm asking for is a determinant. The determinant of 1, 0, 2, 1, 1, 3, 1, 2, 2. So what the formula says that you're supposed to do is take this number and multiply it by the determinant of these guys. 1, 3, 2, 2, minus this number times the determinant of this one right here. 1, 3, 1, 2, plus 2 times the determinant of that little matrix right there. I chose 0 on purpose, so I wouldn't have to do this set of computations right here, because it turns into 0. So this isn't hard, it's just annoying. And many of these computations are like this. Okay, so if you're going to keep going, you would write 1, and the determinant of this matrix is AD minus BC. So A times D minus B times C minus 0, because this was 0 times prepared, plus 2 times A times D minus B times C. That gets you 1 times, what, 2 minus 6 is -4, minus 0 plus 2 times 2 minus 1, which is 1. So you get -4 plus 2, which is -2. If you care, that means that this matrix has a multiplicative inverse. You could divide by it in some sense. But for us, we're going to be using this to produce cross products.
Can you go over quickly one more time the second term in that, which matrix you're using, the 2 by 2?
I noticed that looked a little confusing. Hold on a second. I'll look at it again. So this term right here.
Yeah.
This is the number that you're going to multiply by. And to get the matrix, you take the determinant of, you eliminate that row and you eliminate that column. And then the 1, 3, 1, 2 is what's left over when you do that.
Okay, makes sense.
Yeah, so this is like what's left over once you eliminate that row and column. Okay, now that seems like an awful lot of busy work for not a lot of reward. But it turns out you can use the determinant to record the formula for the cross product. Namely, if A is equal to A1, A2, A3, and B is equal to B1, B2, B3, then A cross B is the determinant of the matrix where you put I, J, and K up here. Those are the unit vectors in R3. A1, A2, A3, B1, B2, B3. And when you compute this, you get the exact same formula that we wrote out. This turns out to be equal to the original formula we wrote, which is A2, B3 minus A3, B2, I minus A1, A3, not 1, A3, A1, B3 minus A3 B1 J plus A1 B2 minus A2 B1. Okay. So notice, so we haven't, this actually has not come up in lecture yet. Is there anybody who's not comfortable with this IJK thing? I mean, most people have seen the vector stuff exhaustively in their past. So I need to explain, I mean, is there anybody who's never seen the IJK version of this before? Okay. Okay, the idea is that this is the x coordinate, y coordinate, and z coordinate of something, right? But this is the same formula we started the class with. So normally when you compute a cross product, you don't remember this formula. You remember that you're just taking a determinant of some matrix. Let's do an example. I'm not trying to race, by the way. It's just I don't want to belabor something that's basically algebra. Okay, so let's let A be equal to the vector 1, 0, 1, and we'll let B be equal to the vector 0, 1, 1. Then we'll compute A cross B. So A cross B is the determinant of I, J, K, and then you put the entries of A into the matrix, and you put the entries of B into the matrix, and now you compute a cross product, or a determinant. So if you do that, you're going to get I times 0 times 1 is 0 minus 1 plus J times the determinant of the matrix made out of these bits here, 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 and here, which is 1 times 1 minus 1 times 0 plus K times the determinant of this matrix, which is 1 times 1 minus 0 times 0. Which gets us minus I plus J plus K. Yep. Did I make a mistake? Where? Oh, yeah. Yep. Yeah, minus the middle number. Minus the middle number times the submatrix. That's the only obnoxious thing to keep track of when you're taking determinants is plus, minus, plus. Okay, now, if I don't want it in component notation like this, I can write it down in coordinate notation as the vector minus 1, 1. Now, there's something weird that happens. If I take this vector that I produced, so this thing right here, what you would say is, oh, the cross product of A and B is equal to the vector minus 1, 1. This is why we call it a vector product, right? Two vectors go in, you multiply them, and a vector comes out. Now, what is the main reason why we do this? Well, what happens if I take a dot product of this vector with either one of the original ones? If I take A, and I take its dot product with this, that's the same as 1, 0, 1 dotted with minus 1, 1. I know how to compute a dot product. I just take first times first plus second times second plus third times third, which gets me 1 times negative 1 plus 0 plus 1 times 1, which is minus 1 plus 1, which is, 0. So the cross product is perpendicular to A, right? The thing that we produced here, this vector that we produced, when I take the dot product with the original vector, I got out nothing. That means A is orthogonal to A cross B. The dot product being 0 tells us that it's at a right angle. Likewise, if you do this for B, is B dotted with minus 1, 1, and you get 0, 1, 1 dotted with minus 1, 1, 1. First times first is 0. Second times second is -1. Third times third is positive. Oh, it's 0 again. So A is perpendicular to A cross B, and also B is perpendicular to A cross B. So this is a way of taking in two vectors. This is the other big use of the cross product. In fact, what the book says is the most important use. The cross product is a way of taking two vectors in 3 dimensions and producing another vector that points orthogonally to them. So why does this come up in physical applications? And what the picture would look like is, suppose you have two vectors A and B. Any two vectors sit together, I mean, as long as they're not on the same line, any two vectors make a plane, right? You can imagine on the table here, I've got one vector pointing this way, another vector pointing this way. They sit together in the plane of the table, right? And what the cross product does is it gets you a vector perpendicular to the whole plane, not just A and B, but the entire plane has the cross product sticking out of it as an orthogonal vector. So A and B don't have to be perpendicular to each other, but the thing you get out at the end is perpendicular to both of them. So this turns out to be incredibly useful when you start studying vector functions, because it gets you a way of talking about these, like, I mean, this is, I'm going to use the word here, what's in physics a lot of times called a normal vector. A vector that's perpendicular to another collection of vectors, right? This is its main use is in physics in a lot of cases is producing vectors that point normally to some surface or curve. So we'll see this in calculus when we get there. Okay. Now this isn't just true of these particular vectors that I've chosen. This is the general, I'll even dignify this with the name theorem. The theorem says if A and B are non-parallel vectors. Okay, I'm going to use this fancy symbol here that just means 3 dimensions. If A and B are not parallel in R3, then A cross B is orthogonal to A, and A cross B is orthogonal to B. If they are parallel, then you end up with the determinant turns out to be 0. It produces no vector. You should check that. So the big question here is, what if they were parallel? And my answer is going to be, go compute dot product. Sorry, cross product. All right. Right, so we have another theorem here. The dot product tells us when things are the dot product. The dot product has these properties, right? That if A dot B was equal to 0, then A was perpendicular to B. And we had the formula that said that the dot product told us about the cosine of the angle between two vectors. The cross product has a similar geometric interpretation. So if the cross product of two vectors is 0, that coincides precisely with the case that A and B are parallel. A and B are parallel whenever the cross product is 0. Now remember, 0 here means sort of the 0 vector, but pile of zeros is still 0. And then I'm going to write down this formula. The length or magnitude of the vector A cross B is the length of A times the length of B times the sine of the angle between them. So cross products tell you also about angle, but they tell you about parallel vectors, where the dot product tells you about perpendicular vectors. Okay. So all of this stuff is sort of the beginnings. You should think about this as these are the basics of what's called vector geometry. And the reason that you want to study vector geometry is because physics problems are defined in terms of things moving in three-dimensional space. So you need to be able to take problems that are in terms of vectors and pull them out into useful right-angle decompositions, right? So the thing that you've seen in the past with these ideas, secretly in the background, every time you took a force and you broke it into pieces that were pointing in a right angle to each other, a gravity and a normal, you were using these, but they just didn't tell you. They made you learn some sort of conversion formula with sines and cosines, right? But every single time, for example, an example of you using this, this is really what's going on. In force decompositions. Is that you're taking a vector and you're pulling it apart into components that are at right angles to each other using sine and cosine. Right? So you might want to bring any bad memories back for anybody, but if you've dealt with, like I said before, we've got a problem where somebody's pulling, or oh, the box is being pulled down the ramp with a force of 100 newtons, and you've got one piece that goes this way and one piece that goes this way. So, oh, decompose that into the gravitational force and the normal force. You're literally just doing formulas that come from that. And you could have been taught this, and maybe you were, in the language of dot and cross products, dot products at least, and cross products in 3 dimensions. So I've actually used the question: are you taught the vector notation for this, or they still give you the t naught cosine theta, t naught sine theta version? No dot products? Oh, that's so sad.
They teach me dot products after my physics right now is teaching us dot products.
Sweet.
After we learn force geometry.
It's all easier once you actually learn linear algebra, it turns out. Okay, so last thing I want to say before we close this down for the day is, after we're done sort of building up, I know this section of this chapter probably feels really dry because we're just building this basic machinery instead of applications of it, right? We're not doing calculus right now, we're doing arithmetic. But we have to have this language down so that when we start doing calculus, we've got tools to work with. Okay? That's really what we're after. It's a language we can use to do calculus for functions that spit vectors out. And so one thing you might ask is, what justifies calling this a product? Right? So why do we even call A cross B? Like, why is this a product? And the answer is, it satisfies a distributive property. So if you have A cross B plus C, you have two vectors that you've added, you cross A with them. The parentheses here are trying to, this is a distributive property, right? A times B plus C. Then it distributes the way that you think it should. A cross B plus A cross C. Determinant. Cross. A goes in and hits this with a cross product, A goes and hits this with a cross product, and then you add the cross products of the two pieces. All right, what else do I want to say? There's a more interesting one, I think more interesting one, which is this one. So this is called, this has a fancy name, the scalar triple product. If you start with a vector A and you dot it with the cross product of two vectors B and C, it's a triple product because there's three things that have been multiplied with two different multiplications. But the thing that comes out the other end of this is a scalar, right? Vector cross vector is vector. Vector dotted with vector is scalar. This is a number that comes out. This is a vector. This is a vector. All of it all together is a scalar. But this is a special one. part of the reason why this is special, oh, I should point out first, this is a weird one. This is A cross B dot C. Look at that. So it's associative, but by switching the multiplications. And you should be really, this should make you suspicious, right? Like, wow, how on earth should that possibly hold? But the awesome thing, this comes up all the time because what this measures, this thing measures the volume of a parallelogram. This measures the volume of the parallel pipette that spans A, B, and C. So frequently in applications, you break problems down into pieces that are like A, B, and C. Well, in the same way that B and C could be used to form a parallelogram, A, B, and C together can be used to form a parallel pipette. A parallel pipette. There's a sweet word. And it turns out to be the case that A dot B cross C is the volume of that. All right, there's a lot of basic arithmetic involved in scalar and cross products. When you do the homework, make sure you do enough repetition to be comfortable with this. If you're